All right, so page 299. Okay.
299. Stoichiometry. Hey, that's number. Introduction to stoichiometry. Stoichiometry. Which 9 was Introduction to stoichiometry.
And oddly enough, a lot of you are saying introduction to stoichiometry. We've already had an introduction to that, but not for the reason that you might think. Okay, so on page 299, most of our knowledge of chemistry is based on careful quantitative analysis, substances involved in chemical reactions. Now, even doing your qualitative analysis, 2 weeks ago, 3 weeks ago over in the lab, a lot of you, well, not a lot of you, it's one of those aspects to where it would come with experience that some of you actually had iron and then just didn't know it. But the hint was so, what do I want to say, subtle, it really wasn't that easy to see. But when you would add that ammonium thiocyanate, that was the compound to it, okay, what would happen to your solution? Yeah, it would actually turn blood red. And then when that happens, I thought maybe there's something interesting out there. Okay. But so when that happens, a chemical reaction was actually taking place, and that was an indication of which ion. Do you remember?
Iron.
Yeah, it was iron. And which would make sense because, does anyone know what hemoglobin is? Yeah, we've all heard of it probably. Just never really had to apply it because it has iron in it.
Isn't that the iron in the blood?
It's the iron in your blood. That's what makes blood red, is with that. Okay? So if clay has iron in it, typically it's going to be what color then? Probably a type of shade of red. Okay? So we've had some exposure to this, but perhaps not for the reasons that you might think. Okay, so going past our qualitative analysis, composition stoichiometry, which you studied in Chapter 3, and not just Chapter 3, but also Chapter 7. Okay, I don't know if it goes on to state, no it doesn't. Okay, deals with the mass relationships of elements in compounds. Okay, so when we talk about reaction stoichiometry, involves the mass relationships between reactants and products in a chemical reaction. Okay, so one of the aspects that we've talked about in the past is, okay, we'll just keep it simple with a synthesis reaction. Would give what, do you think? Okay, sodium chloride. So now, of course, we need to write out the reaction, which we all know sodium is what? Nah, it can't be.
I bet it is, though.
Nah, it can't be.
Well, it ain't CL.
Oh, Na. Yeah, nah, it can't be that.
Couldn't be.
Couldn't be. Yeah. Yep. Okay. Keeping your head warm. We got to keep all them brain cells warm. Okay. All right. Okay. Then. Okay. We're sleeping. Cl2. Why is that?
Diatomic.
Diatomic. Okay. Then. Okay. So -1, +1. So that is fine.
2, 1, 2.
Okay. We've got 2 chlorines here, so we got to get 2 on this side, which means then we have to put a 2 there. Okay. So when we're talking about composition stoichiometry, perhaps we would say if we had 90 grams of sodium chloride, Maybe we want to know, well, what's the composition of just sodium only in that compound? Okay, so you're only referring to what's on this side of, you're not even having a reaction because you're not illustrating anything with that. Because what did we say with that of reaction stoichiometry? Okay. Okay, we've had our fun. We've tied it. Okay. I don't know. Maybe you're going to go hop out on your hog out there. I don't know. Okay. It's not a hog for what people think. Just because you have a motorcycle doesn't mean it's a hog.
Oh, he's gonna go on the SRT.
No, it's you're part of the Harley ownership group. That's what makes it a hog. Okay, that's why people say, "Did you ride your hog today?" No, I didn't. He's back in the barn. But, okay, so all right. I just told you where it's at. It's back in the barn. Oh yeah. No, actually, I winterized it already. Put the old stabilizer in it, pulled the battery out. Yeah, that way in the spring, put the battery back in, keep our fingers crossed, and then it takes off again. Okay, so reaction stoichiometry now, okay, involves the mass relationships between reactants and products, hence a chemical reaction. It sure must be fun playing with that because it's making its rounds from there to there to there, but no. People know I'm bald. I don't need to put that over top to hide it. People know. Oh, well, that's my excuse then. Okay. All right. Reaction stoichiometry is the subject of this chapter and is based on chemical equations and the law of conservation of mass. All reaction stoichiometry calculations start with a balanced chemical equation. This equation gives the relative numbers of moles of reactants and products. Now, going back to our composition stoichiometry, there were shortcuts that you could take, okay? That is true. But we want you to remain consistent. Okay, we're back now. Now that I got the batteries replaced. Okay. Turning the page to 306. Okay. You're not always going to be given the balanced chemical equation. So, do you want to try practice problem number 1 on your own, or is it one you work on together? Okay. So on the top of page 306, it says, ammonia, or NH3, is widely used as fertilizer in many household cleaners. How many moles of ammonia are produced when 6 moles of hydrogen gas reacts with an excess of nitrogen gas? Okay. So it says we've got ammonia gas, or NH3. Oh yeah, I've spent my time on the farm as well. Okay. So you've got a chemical equation here. Next thing you're going to want to do is balance that. Okay. The hydrogens are odd. Let's get these to an even number. Okay, so we multiply that by 2. Okay, so then, and you don't always have to balance your equation first, but I think that's probably a good idea to do that. Okay, so it says how many moles of ammonia. Okay, so how many moles of this? We don't know, because that's what it's asking. How many moles? Okay. Are produced when 6 moles of hydrogen gas. So if we got 6 moles of that, how many moles of this are going to be produced? Okay? So there's only one place to start, and that's with this. So 6 moles of hydrogen. Like you had said, it's just a 2-step problem. So to cancel out that mole of hydrogen in the second step, okay, we need moles of hydrogen.
Are you really?
Kick her out. Are you okay? Kick her out.
Sorry.
All right. So what are we looking for then?
You're looking for your ammonia.
Moles of ammonia. Okay, so every time you have a mole over a mole, what must you refer back to? Am I hitting the equation? Okay, you have to look back at your equation. Is there anything in front of NH3? Is there anything in front of H2? Okay, so these have canceled. That's something I didn't do last problem. But 6 times 2 is 12, divided by 3 gives you 4. Okay, 4 moles of, okay. Practice problem number 2. Oh, I'm sorry. Is there any questions on this problem? Okay, these mole-to-mole problems, pretty straightforward. Yes?
On our, like, when we get a worksheet, is it going to be like, is it going to have us the formula, or are we going to have, like, word problems?
Combination of the two. Okay?
All you gotta do is just look on the table.
Because, as you can see, you're not always going to be given the chemical equation. This is what we like to say all the time. Okay? Okay, so moving forward, do you want to try problem number 2 on your own? Probably not, because that's a little difficult. Okay? Because it says the decomposition of potassium chlorate is used as a source of oxygen in the laboratory. How many moles of potassium chlorate are needed to produce 15 moles of oxygen gas? Now, use your terminology to your advantage. Okay? Use your chemistry knowledge to your advantage, I should say. If you have potassium chlorate, it says it's used for oxygen, right? So that must mean that somewhere over here you've got some oxygen, which you do. So then when you compare that to this problem, it says the decomposition, right? So where this would be a possibility for it to break apart, right? But then we'd have ClO3 over here. That's not the case. You just have oxygen only. So that's not where it splits apart. So where else must it split apart then? Right there. So then this disassociates or breaks apart. You have potassium chloride plus oxygen. Okay? So now you have to balance that. You've got an odd number of oxygens on the left, an even number over here. So how do we get this to an even number? Okay, so now you can proceed. It says, how many moles of potassium chlorate? So an X amount of moles. We don't know. How many moles of potassium chlorate are needed to produce 15 moles of oxygen gas? Okay. So just like every other problem, the only place to start is on this side of your equation. So we've got 15 moles of oxygen. Okay? Then, in just a two-step problem, notice every other time we were going left to right. Here we're going right to left. So to cancel out our oxygen, what do we put down here? Moles of oxygen to moles of, and if you wanted to do that, you could. Just as long as you know that potassium chlorate is this compound, because we're not looking for a mass of it. Okay? So we've got a mole over a mole. So what does that mean as far as the equation is concerned? Is there anything in front of potassium chlorate? There's a 2.
There's a 3 in front of the oxygen.
Okay? So in this case, 15 times 2 is 30, divided by 3. Okay. 10 moles of potassium chlorate. Okay. Okay. Turn to page 308, and then we're just going to do one practice problem. Then we're going to stop there for today. So, I'll let you pick the first problem or the second one.
Second.
Okay. What mass of glucose can be produced from a photosynthesis reaction that occurs using 10 moles of carbon dioxide? Okay. So we already know that we've got that over there because we're producing that, correct? Well, plants give off this as a byproduct, right? So what do plants absorb from the ground? What do plants absorb from the ground?
Water.
Okay. what do they absorb from the air?
Oxygen.
No, carbon dioxide.
Well, I hope not, or else your Rubisco enzyme isn't functioning correct. Okay?
Not to get one of
But I've been fast.
So we've got 6 there, a 6 there, and also a 6 here. This is the devil's reaction. It is. That's right. Yeah, you've got that. Okay. But no, 666 is just a number. Okay? So what mass of glucose? Well, again, we don't know. Okay? Then can be produced from 10 moles of carbon dioxide. So you're starting with 10 moles of that substance. Okay? This is no longer a two-step problem. And if you want to try to do that, I don't know why you would, but
Top left, you gotta put some carbon dioxide.
okay, maybe. The only place to start is with this. So we've got 10 moles of carbon dioxide.
You gotta have 6. Or no, not. Then you gotta have some more carbon dioxide.
Then you're gonna have on the bottom,
Moles of carbon dioxide.
Notice we're making that line just a little longer.
6 moles of carbon dioxide.
Okay, let's count. You're not wrong. Okay, for every mole of carbon dioxide, we want to get to this side of the equation now. And the only way we can do that is with a mole ratio. Okay, so moles of what do you think? What are we looking for? Now, you can do this, but you better be careful. Yeah, I'll explain why in just a moment. Okay? Is there anything in front of CO2? That's 6 from that one. Is there anything in front of this glucose? There's a 1, so we can just leave it like that. These have canceled. Now, how do we get rid of this mole of glucose? And then this is where you have to be careful. As long as you know that GL or glucose is that formula, you can go ahead and do that. So I haven't even worked this through. See, I get to cheat. So I'm just going to write 300 over there.
I'm guessing that's probably pretty accurate.
Well, we'll see. Okay? Now, it's one thing that sometimes algebra books, geometry, chemistry books, they'll show you what the answer is or tell you what the answer, but what good does that do if it doesn't show you how to do that? Okay? And that's what we're trying to illustrate here. So, we've got 96 from the oxygen, 16 times 6. We've got 72, 12 times 6. Actually, we should probably put 0, 6, and then 12, 12. This marker's about had it. And I think you get somewhere around 180, correct? Okay? 180 grams of that substance. These have canceled. Okay? So, 1,800 divided by 6 is what? So 10 times 180 is 1,800 divided by 6, just like what we predicted. 300 grams of glucose. Okay, I think that's good enough for today, so we will catch up to you next time. Now, remember, if at any time when this gets to be a little difficult, you wouldn't have to watch the entire aspect of it, but you can say, well, I don't remember why we did that. You can always go back to Science Channel, figure it out pretty quickly. Okay, we'll catch up to you next time.